So it should be recording the lesson at this time. Hopefully my computer doesn't go to sleep, but we'll see. All right, so let's go ahead and get started. Good morning again. Just so you're aware, I sent a message on Google Classroom. You gotta keep track of that. Yesterday, there's a possible or probable mini lab activity today. So I did ask not to wear Crocs. So if you are wearing Crocs, you'll just watch from the side, but it won't count against you. If you have an additional pair of shoes, you can switch shoes, but you shouldn't be wearing Crocs during the lab. And you will also need gloves and goggles because you'll be working with acids and bases and little droppers. And if something shoots into your eye, it's going to hurt. And so you will need gloves and goggles today. And so let's go ahead and get started. We have a big topic today. We're going to be learning about buffers and buffer systems, which has to do with acids and bases, but they're really important. So first off, let's go over the bell work. I saw that many of you did quite well on this bell work. The homework. Remember for the homework that I allow you to leave one, maximum 2 parts blank, 2 questions blank, and I'll still give you the stamp. I know that there were some people that were very confused about the percent ionization question. So remember, if there's a specific homework question that you're confused about, and after I post the answer key, you're still unsure, remember to come ask me at tutoring, or you could do it during a bell work if I have the time. Yes.
We're allowed to do that?
To do what? Leave 1 or 2 parts blank. Yes, max. If you leave like 2 pages blank or a page blank, then you're not going to get credited for doing the assignment on time. But if you have like 1 or 2 parts, like a part A, part B, that's okay. I know that some people left the percent ionization blank because didn't understand it. But you can ask me about it. It's actually not that crazy of a thing, but you may be able to pick it up from the mark scheme when you see it. All right, so write the expression for the Ka of CH3COOH. So let's go ahead and take a look. It's going to be products over reactants. So what would that be? They didn't give you the equation, so some of you can just visualize this equation in your head, and I saw some of you doing that and not writing it out. But that's the equation that we use to put together the equilibrium expression. Products over reactants means CH3COO minus multiplied by H plus, not added, divided by CH3COOH. It's really important that you do get these equilibrium expressions correct because they are how you solve the question. So if you don't get the expression correct, you're not going to solve the question correct. Yes.
We don't need like the state matters. What matters?
No, not for the equilibrium expression. You don't. You can write it out here. It's AQ, 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 and that's just to tell you that yeah, they all count. There's no liquids or solids here, so nothing would be left out. Everything should be included here.
And also,
Yes.
you can't do like CH3COH or like just CO plus and then OH minus.
Did you say CH3CO?
That's it. Just CH3CO plus and then OH minus. Does that not work?
No, because it's not a base.
Okay.
If you said OH minus, you'd be saying that it's a base that breaks off, but it's an acid. So they're telling you it's Ka. A means acid, which means H plus. It has to be H plus in the product. Yes? Makes sense? Okay. I'm glad you're asking this question. Please ask the questions because they're going to be the things that separate you from getting the answers right or wrong. All right, so number 2. This is a math question. And you can either just straight up use the formula I gave you last class, or you can create the equilibrium expression. Either way is fine. The formula I gave you last class was Ka equals H plus X minus HX. That was the formula I gave you. Where X in this case would be ClO. So we want the pH, we have the concentration of HX, and we have the Ka. So we plug in what we know and we solve for what we don't. I think this question was scored pretty well on all the papers that I checked. 3.72 times 10 to the negative 8 equals, these two are the same, right? And this is 0.010, so what do I put up here? Can I put up there? X squared, where X is going to give me my H plus concentration. So then I have to algebra this out. So to algebra this out, I multiply by 0.010 on each side, and I get 3.72 times 10 to the negative 10 equals X squared. Then I'm going to take the square root of both sides. Take the square root, and I get 1.93 times 10 to the negative 5. So what does that equal? X, which is my H plus concentration. So to wrap it up for the pH, what do I got to do? Negative log it. And that gives me my answer, which is 4.71. This was actually a question in the homework, wasn't it?
Oh.
Yeah, actually, like,
This was a question in the homework.
two off because like it goes by like
Sometimes, every once in a while, I'll give you a question that's in the homework. Frequently, you did the homework right. All right, continue. Number 3. This is one that's from a very recent test. So I was interested to see if you all would get it correct or not. And many of you did get it correct, which was impressive. But I think it partially is because we have done a lot of labs that ask similar types of questions. And so first, 2 marks here. If Cambridge wants to bless you, they give you something like this. What do I mean? They're telling you to show what the answer is, meaning they're already telling you what the correct answer is. Hey, just come up with how do we get that? And so this last year's paper for in May, June, kids came back and said they gave us the answers and just asked us to show how it was done in several questions. That means that they're making it easy, but that also means the grade threshold becomes higher. It means we need more points because they made it easier, so more people are going to get it correct. So anyways, they give you compound B, it's a hydroxide of a group 2 element, and they tell you it's strong. That's important because strong means that you're going to directly be able to use the pH formulas, that you do not have to do an equilibrium here. And then it tells you an amount of grams of B is dissolved to make 250 centimeters cubed of solution. Solution F is a pH of 13.09. What is the concentration of hydroxide ions? So there were a couple different ways you could go about it, and Cambridge said you could do either way. The easiest way to go about this is to change pH to POH. How would you do that?
13.1.
So 14 minus 13.09 equals 0.91. So you can find the POH this way, because remember, POH equals 14. So if you subtract 1, you'll get the other. And then you can take 10 to the negative 0.91, and that'll actually give you the concentration, which is 0.123. And that's it. That's it. 2 marks. That's all you had to do for 2 marks. Question? Question? Okay? Okay. Alternatively, you could have changed the pH to H+, changed the H+ to OH-. Remember, there's multiple different ways that you could solve these questions, but you should have came up with the 0.123 answer at the end. The next question is the one that I thought maybe you might get tripped up on. They said, why is compound E a different molarity? It's not 0.123, it's 0.0615. So what you had to recognize here is, first of all, 0.0615 is a half of 0.123. That's the relationship. This is half, which means that one of my compound has 2 hydroxides, and that's what you had to prove. That's all you have to say. Because there's a group 2 element, a compound of a group 2 element, there are 2 OH- ions. in one of the compounds. Because it is a compound of a group 2 element, there are 2H minus ions in one of the compound. This means your concentration would be half for the compound, but that's all you had to say. And so then the final mark, and it was only one, is to use the concentration given in 2 to identify compound B. So how would we go about that? And for me, I felt like this is more than 1 mark worth of work for me, but they only gave you 1 mark if you figured it out. So this is actually very similar to what we did in the lab. We would have to know, okay, to find this out, we're going to have to figure out the molar mass. And the molar mass is defined as grams over moles. So they gave us some data. They gave us the moles in a dm cubed, and they gave us the grams, but not in a dm cubed. They gave us the grams in centimeter cubed. So what could you do here? Does anybody have a suggestion?
0.061554.
That's one of the methods. So you could, and I did kind of the opposite. I said, okay, if they're both in a decimeter cubed and this is 250 centimeters cubed, that means that if I want to make my volumes the same, I could either change my 250 centimeter cubed amount to 1 decimeter cubed, or like you did, change the 1 decimeter cubed amount to the 0.250. So what I thought was, okay, if I change this to 1,000, if I said this was 1,000 instead, which is the same thing as 1 decimeter cubed, then what would the amount of grams be? It would be multiplied by 4 to keep the concentration the same. So what I did was I said, okay, so I'm going to multiply this by 4, and this is now 10.52 grams per decimeter cubed. Why does that matter? Well, to find the MR, if my volumes match, I can just cancel them out. So if this is 10.52 grams over dm cubed, and that's 0.0615 moles over dm cubed, guess what happens to the dm cubes? They just cancel, and I get the grams over the moles, as long as my volumes match. Whichever way you make your volumes match doesn't matter, as long as your volumes match. Kind of make sense? And so my MR here I got was 171 for the compound. So what would we do next? Start subtracting out the 2 hydroxide. So it'd be 171 minus 32 minus 2, 137, which tells me barium. But if I write barium, I'm not right, because it's asking me for the entire compound. So the correct answer here is BaOH2. I feel like this is these distribution of marks on A-level tests are weird to me, because this was worth 1 mark, but I feel this was a significantly more amount of work than what was worth 2 marks up here. So the distribution of marks is always a little bit strange in this paper. Yes. Because I needed to make the volumes the same, and they said that this is the moles in 1 decimeter cubed, and this is the grams, but not in 1 decimeter cubed. 250 centimeters cubed is a quarter, 1/4 of 1,000 centimeters cubed. So if I said I had this many grams, 2.63 and 250, my train of thought was, okay, well, 1,000 is 4 times bigger than 250. So I related those two, and I said, if that's 4 times bigger, then my grams must also be 4 times bigger to make the volumes the same. That's why I said, to me, this thought process requires like more thinking than that thought process does.
I did like it in a way different way. I don't know.
Yeah, but if you came up with the same answer, if you used a different pathway, if it makes logical sense, then it works. So it would just, I'd have to just check your work, basically. What you see with the pH formulas is there's like so many ways to solve it. I could give you one method, but you can come up with other methods to get the same answer. All right, so that was the bell work. Let's see if we can do this lesson in an hour today. We'll find out. This lesson actually has 2 parts. Today we're going to do buffers part 1 And on Friday, we're gonna do buffers part 2. So today we're gonna do the intro to buffers, what they are, and if we have the time, which I'm really hoping we do, you'll get to make a buffer solution today. And on Friday, we're gonna look at the more complicated examples, the more complicated math. Sorry, but I did break it into 2 parts for that reason. So what we're gonna do today is we're gonna define what a buffer is. We're gonna explain how it can be made. We're gonna explain how it controls pH using chemical equations in our explanations. Yes, you have. Describe and explain the use of buffer solutions, including the role of the bicarbonate ion in controlling the pH of our blood. And then we're gonna calculate the pH of buffers. So a few things to get through today. It's not a ton of objectives, but like I said, this is gonna have 2 parts. And so let's go ahead and get started. In acids and bases, this is a topic that should be brand new unless you've studied chemistry on your own. Buffer solutions are solutions where the pH does not change significantly when you add a strong acid or a strong base to that solution. So if I add a small amount of strong acid or a strong base, the buffer solution will maintain the pH. It won't change very much. Why? Go ahead. So let's say that we have, and I'll do HClO and ClO minus. This is an example of a buffer system. This is a weak acid. And this would be its what? Its conjugate base. So sometimes you're going to see it called a conjugate base, and sometimes you're going to see it called a salt. Why would they also reference the conjugate base as a salt? It's a salt if there's a positive ion in the solution.
Because when you eat it, it tastes like salt.
No, don't eat it. Because NaClO would be bleach. I guess fun fact, but I don't know how I feel about that. But anyways, a buffer solution is comprised of a weak acid and its conjugate base. And so what happens if I were to add a strong acid into this existing solution? What would happen? So if I were to add a strong acid, would the acid react with acid or would the acid react with the base that's present? It would react with the base. So the idea is that if I add, I'm just giving you a heads up. If I add, and I'm going to change the color, a strong acid, HCl, HNO3, H2SO4, whichever, what's their reaction going to do?
It's gonna be this.
It's going to react with the ClO minus, and what is it going to do? If I add strong acid, the reaction will shift to the reactant side and basically absorb that H plus and put it together into HClO, which will not change. So basically, this reacts with the H plus, so the H plus is not free in the solution. If it's not free in the solution anymore, the pH is not really going to change, at least not very much. And so that's the concept behind what's going on here. So a buffer solution is one that is comprised of either a weak acid and its conjugate base, or a weak base and its conjugate acid. So you can have acid buffers and you can have base buffers, but both parts must be present for this to be a buffer. So both must be present. And if one of them is no longer present, then you no longer have a buffer. And so what's going to possibly happen, that we'll see next class, is what if I added so much strong acid that it reacted with all the ClO minus in the solution? What would happen? If all of this is gone, then you can't make this anymore. And what would you have left? Just the strong acid. We call that destroying a buffer. And today, like I said, if we get the time in the lab, you know, you can play around with that. You can make a buffer and then work on how you can destroy that buffer. Meaning it won't work the way it's supposed to anymore. So what is the purpose? It keeps the pH around the same. Now, around the same does not mean a pH of 7. And some people get confused of this. There are buffers that keep a pH at 3, buffers that keep a pH at 4, buffers that keep a pH at 5. It depends on what the chemicals actually are, what the actual pH of that buffer system is going to be. Yes.
Does the pH of the solution is it dependent on the pH of the water?
It's dependent on the Ka of the weak acid, like what the actual pH of the buffer would be. Whether it's a lower or a higher pH. Depends on how much is ionized. All right, are we good so far? All right, that's just a brief introduction. This is actually a definition that needs to be memorized, and it is a common definition. Meaning I've seen this on so many tests. Paper 4s. A buffer solution is one in which the pH does not change significantly when small acids or alkalis are added. You can also say it minimizes the change in pH. It's not that it doesn't change at all. It changes just a little bit because as the acid is added, it reacts with the base to, instead of have strong acid, it turns it into a weak acid. All right, so has to do with something called Le Chatelier's principle. So the action of buffer action has everything to do with Le Chatelier's principle because we've got a weak equilibrium. And every time we've got double arrows like this, that means Le Chatelier's principle is at play. Meaning if I add anything to either of the sides of the reactions, the reaction will work to minimize the stress by producing the opposite. Meaning if I add acid, like I add acid, what the reaction is going to do is go, oh, I'm going to go that way. And if I add base, the reaction is going to go the opposite direction. And so weak acids have an equilibrium, meaning if a strong acid is added, then according to Le Chatelier's principle, this reaction would shift to the reactant. Because H3O plus would be strong acid. Because that's the strongest acid you could have with water. As long as there's still some weak acid and salt left, the buffer will work to neutralize strong acids and strong bases. So as long as I have both components of my buffer, it's still going to be able to neutralize a strong acid or a strong base. This is actually the one that you're going to make today. This is ethanoic acid, and you'll have sodium ethanoate. But if I have an excess of strong acid or strong base, and it reacts with everything, you destroy the buffer. And next class, we're going to work on the math of that. Today, we're just talking about the idea. So let's take a look at a couple of practice questions, just so you can start to see, and this is from the textbook, what's going on here. They tell you a mixture of a half a molarity of aqueous ammonia and a half a molarity of ammonium chloride acts as a buffer solution. So what is ammonia? What's the chemical formula for that? We do have to have that off the top of our head. And what's ammonium chloride? NH4 plus, Cl minus. I want to bring something up right here. This is a salt. Why? It's a salt. It's an ionic compound. If you were to look for it in our laboratory, we have it as little granules. It is an ionic compound. The Cl minus is going to confuse you when you do reactions, most likely, because it's technically a spectator ion. The only thing that matters for the buffer is the, in this case, weak base and the conjugate acid. The other part of the salt, the other ion that's there, Cl minus, Na plus, whatever else is there, isn't actually going to be part of the reaction. And it's technically a spectator ion in the solution, which is why I said, actually, if you write it, you might actually get confused depending on what type of question that you're doing. For this first set, you will be able to write it and you'll be able to get the answers and understand them. But as we go through, I'll explain further. Yes.
Wasn't chloride ion be a base?
The problem, it's not going to accept H plus. Why?
Oh, because
Because it's going to redissociate immediately because of the strong acid. It's something that comes from a strong acid, so it would stay dissociated in solution. It's not going to combine and stay with the H plus to answer your question. All right, so let's take a look at what's being asked of us. It says explain, this is funny, explain by use of equation. So you're not really explaining with words. You're explaining with the chemical reaction. How this buffer solution minimizes the changes in pH in addition of dilute hydrochloric acid. So hydrochloric acid, would that react with a base or an acid? That's the first thing you have to ask yourself. 1, does this react with the acid or the base? With the acid part of the buffer or the base? And if you follow these steps, it's not going to be that difficult. So does this react with the acid part of the buffer or the base? Well, if something's an acid, it's going to react with a base. So the answer is the base part of the buffer. Then you have to identify, well, which of these two components, the NH3 or the NH4Cl, which one is the base? NH3. So we know it's going to react with the NH3. So second, write the reaction. So NH3 plus, they told us dilute hydrochloric acid, HCl. Write the reaction. So what does that make? Literally the other part of the buffer, NH4Cl. So when HCl is added to NH3, the HCl is reacting with the NH3 and producing NH4Cl, which is the other part of the buffer. That's all you have to do. So far, so good? Let's try the second example. What if instead it was dilute sodium hydroxide? The first thing you have to identify, well, a sodium hydroxide itself, is it acid or base? What is it? Does this react with acid or base? It's a base, so it reacts with an acid. So what is the acid part of the buffer? NH4 plus, and we can write the whole thing, NH4Cl. NH4Cl. So what am I going to do to complete this reaction for part 2? NH4Cl plus what? NaOH. And what does it give us? NaCl. And is it NH4OH? You may want to write this little note on the top for yourself. This is actually from AS Chemistry and is still expected that you recognize. If you have NH4OH as a product, that actually breaks down to become 2 products. Those 2 products are NH3 and water. Do you remember the other one like that we have to know by heart? It's going to show up in this lesson too. H2CO3. You have to recognize whenever you're going to produce that, like that shows up as a product in your reaction, you're not actually supposed to write that as the final answer. You're supposed to write what it actually breaks down to become, which is carbon dioxide and water. Similar. They both break down to form water, and then the first one is ammonia and the second one is carbon dioxide. Okay, so what is this? NH3 plus H2O. So think about that. I reacted the ammonium chloride with the sodium hydroxide. I came up with salt, water, and the NH3. So when I reacted this component of the buffer with a strong base, I ended up with the NH3, the other part of the buffer. So each part of the buffer will react with either the strong acid or the strong base to make the other part of the buffer. And whether you wrote the NaCl or not, technically doesn't matter because those two are called spectator ions. And so if you chose to leave that out, on most Cambridge questions, they would accept it. And you'll see Cambridge questions later on where you do not need to write the spectators. Are we good to continue? So, next question. This is from paper 4 because almost everything here is from paper 4. Solutions containing a mixture of HNO2 and NaNO2 are buffer solutions. Why? This is a weak acid. Why is it not a strong acid? It isn't HNO3. HNO3 is strong, right? They're trying to trap you up. This is HNO2. It's a weak acid. NaNO2. Why is that the other part of the buffer? It's the NO2 minus itself is the conjugate base. And then together this is a salt, which is why I said you'll either see them reference it as a conjugate base or a salt, depending on if you see the sodium there in this case or not. If the sodium's showing up, we'll call it a salt. If the sodium's not showing up, we would just call it the conjugate base. They're both the same. So then what is the definition again? A solution that minimizes change in pH. A solution that minimizes, and that's the first point, change in pH. I'll get the door shortly. And then the second mark is to say when small amounts of, welcome back. Did you all try to describe that buffer? Wait, I hit.
Speak louder.
What happened?
One second, are you breathing today?
What?
So it's fine.
Green.
Did you actually?
Okay.
So you,
So you need to be-
are you
We'll
feeling
do the
fine?
buffer solution, all right? So it's a test. If it's what's it called?
Think of the,
You know,
how do you
you
feel?
can test around 10 times.
They're still
Whether
working
it's-
on optimizing your lab.
And
All right.
that's
When small amounts,
pretty actually 20 times.
acid or alkali are added. Just a formal definition, 2 marks. 1 point for minimizing change in pH, 1 point for small amounts of acid or alkali are added. So, did I say this is a common definition? Yes. Would I put this on a flashcard? Yes. Is it likely I'm going to put it on your first test? Probably. It'll probably be there because it's a pretty popular definition. It shows up on many old exams. So study that. The next question. Write 2 equations. Hold it. That show how a solution containing HNO2 and NaNO2 acts as a buffer. So when they say this, it's another very common type of question. What they're saying is your one equation should be react with strong acid. And your second equation should be react it with strong base. Now, I have poured over a bunch of old exams and looked at a bunch of mark schemes. And you can either point out what strong acid or strong base you want to use is. So say, I want to use HCl, I want to use H2SO4, but you're allowed to just say H plus and not include the spectator. So strong acid would be H plus, and base is, what do you think? If I don't want to include the spectator, OH minus. And you're allowed to do that for all of these types of questions. Whenever it's write 2 equations to show how the buffer works, one's going to be react with strong acid. You can represent that as H plus. And strong base, you're going to represent that as pure OH minus. All right, now that I've said that, let's see if we can do equation 1. Which part of the buffer would react with H plus? HNO2 or the NaNO2? the NaNO2. Now, should I write the whole thing? Do I need to write the whole thing? I only need to write the NO2 minus. Why? The Na plus is a spectator. It is not part of the acid-base reaction that's happening. It is your choice if you want to include it or not. However, I'm telling you, I've been teaching this class for a while. Students usually get confused when they start to include spectator ions. Because you're like, what do I do with this thing? Because it's just sitting there on both sides. So you don't need to include it. All right, NO2 minus plus what? H plus. And what does that become? HNO2. That's the first one. So what would the second equation be? I want to react with strong base. Which part of the buffer reacts with strong base? The HNO2, right? Weak acid. You write HNO2 plus OH minus. And what will my products be here? So with the H plus, we knew we just had to combine them because the H plus would go into this. What's happening here? What does the base do? It receives a single H plus. So that is going there, right? So what are my products? Water. Okay. And the other one? NO2 minus. That's it. That's all you have to do. Yes.
I'm sorry, it doesn't make sense to put, does those count as a?
Does it count as a what? No.
No.
There's no change in charge. The H plus on one side is also H plus on the other. This would not be classified as redox. It would instead be classified as acid base. Acid base is the exchange of protons. Redox is the exchange of electrons. They are two different processes. This is the exchange of protons.
I'm confused because the NO2 gains a negative charge.
It does, because this is H plus, so this is NO2 minus.
So there was.
It starts with a -1 charge, it ends with a -1 charge. The charge is not changing. Yes? Yes. So you don't have to. But if you chose to, what would you do? If I chose to include NaNO2 in the first one, how would that work? I would probably want to include my spectator for H as well, or else I'm going to start to get confused on what happens to that Na plus, right? So if you did it, I would say, okay, let's make this HCl then. And then that's going to become NaCl and HNO2. But what happens if you do this? NaNO2 plus H plus. This is where students get confused. They write it like this. You know the H goes with the NO2, but what in the world are you supposed to do with the sodium? So it would be HNO2, and you would write the sodium on the side, which is a really weird situation because you're including a spectator ion, but you're not including the spectator ion from the acid. So this is where everybody will always get confused in questions. So I advise not to do it like this. Either don't include the spectator ions or include all of the spectator ions so that you know what's going to happen as a result. Don't leave yourself in a situation where you have some things included, but it's ambiguous. What's the other stuff that's there? I wouldn't do it like that. I think it's confusing. My suggestion is just do it the first way I wrote. I think that is by far the simplest way to go about things. It is the least complicated. And these questions can lend themselves to becoming complicated if you don't want to be. Yes.
If you did it, would they not be wrong or?
This right there, they might, if you include partial spectator ions, but not all of them. Maybe. Ambiguous is my answer. All right, so that was the first thing we need to be able to do is define buffers and be able to write equations for buffers. And so now we're going to go over a couple of important buffer systems. The first one is the bicarbonate buffer that's in the water. So if you study marine science, you'd actually study this topic deeper. And so it turns out that if we have an unpolluted region of the earth, the actual rainwater has about a pH of 5.7. slightly acidic, but not very. So this is because carbon dioxide in the air will dissolve into water and makes carbonic acid. Well, carbonic acid has a pH lower than 7. And so you will have a pH slightly lower than 7. And this is a buffer solution because it's a weak acid. And so it'll maintain the pH of water around the same, unless you have a high pollution area. If you have a high pollution area where you have acids that are being produced into the atmosphere, the pH will be closer to 4. Meaning, just like acid rain destroys the buildings, what's happening is that H plus is destroying the natural buffering system. That is the carbonic acid buffering system. So that's one of the practical applications of buffers. The second one, if you're going into medicine, you'll be very interested about it, the pH in the blood. In our blood, our pH must stay between 7.35 and 7.45. How big of a range is that? That's a very small range. It's slightly basic, it's a very small range. And we have a bunch of buffers in our blood. Bicarbonate's one of them. It is the most important one. We'll talk about it in just a moment. That's what this is here for. Hemoglobin. And then you also have some phosphate in there. And so what happens is in our body, we produce carbon dioxide. And we also have water, right? We produce carbon dioxide when we breathe. We also have water. So the carbon dioxide combines with water to make this, H plus and HCO3 minus. This is called hydrogen carbonate. A certain amount of dissolved CO2 stays in our blood. And this reaction, this bicarbonate buffer that's in our blood, is catalyzed by an enzyme. Enzymes are catalysts that are complex organic molecules. And so it's carbonic anhydrase. When blood passes through the small blood vessels around our lungs, these hydrocarbonate ions will be converted back to carbon dioxide and water, which we then breathe out. And so what happens if there's too much H plus in your blood, the bicarbonate buffer will work to make CO2 that then gets released out. But what happens if there's too much H plus? If there's too much H plus, then it'll react with all the bicarbonate in the blood, destroy the buffer, your pH will go out of range. That's actually a common, I'd say relatively common medical issue that diabetics get. It's called diabetic ketoacidosis. And that word acidosis means that your blood became too acidic. This happens when your kidneys cease to function the way that they're supposed to, and too much H plus gets into your blood. And so the buffering system is the most important. The hydrogen carbonate one is the most important one in the body for maintaining body systems. If a patient or a person goes into the state of acidosis and goes under the pH level of their normal pH, their body systems start to shut down. So their body systems start to shut down, the kidneys, the liver, and then eventually the heart. And then this leads to coma and death. And so this is why when people have diabetes, they have to be on top of their blood sugar. Because if they go into either acidosis or alkalosis and they go off of where they're supposed to be, you could be in the hospital real quick and dead very quickly, actually. So be careful with diabetes is one thing I'm going to say, because diabetic ketoacidosis is a thing. And that's actually how my mom passed away. So I know a lot about that one. So this buffer, super important, FYI. So those are two common applications. And that goes with the bicarbonate ion, by the way. So you're going to be assessed on reactions with the bicarbonate ion. And so this is the last part of today. Yes, Stefan. How much did you? What?
We went to 1,000 milliliters.
Split it into 2. Keep adding. This is the HCl, right?
We tried two different HCLs too.
Did you try a smaller drop? Try a drop into the 50 and then put it as half to make it, instead of 2 molarity, 1 molarity. They're trying. We'll talk about the stuff you might get stuck on shortly. Okay, so the last part of today is actually the beginning of what we have to do next class, which is the actual math to solve sulfur problem. And there are 2 equations you need to be familiar with. You can choose which one you want to remember, because technically they do the same thing for you. They will solve for pH calculations. This is actually, I can manipulate this using algebra to become this equation. Actually, these 2 equations are the same thing. And so some students will choose to remember the first one, and some students will choose to remember the second one. This first one is the relationship between pH and the concentration of your salt and your acid. Now, notice I said salt here, but what did I tell you that you could instead call that? And you're going to want to point it out. Anytime you see salt in an equation, instead we could reference that as the conjugate base. And that's the weak acid. And so here, this would be the acid and the conjugate base. And you're going to make a decision as we work through questions on which of these 2 equations you would like to use. But take a look at the first one. It says pH equals pKa plus the log, yes, logs are here again, base 10 of your concentration of your salt or your weak base over the concentration of your acid. It's a balance between the 2. The more salt I have, the bigger the top is going to be. The more acid I have, the bigger the bottom value is going to be. And if you remember log, what's the log of 1? You may want to write that out. That means if my salt and my acid concentration are the same, my pH is simply just going to equal my pKa. And then it'll change a little bit based on how much salt or acid I have. That's equation number 1. It's called the Henderson-Hasselbalch equation and will be commonly used in advanced chemistry classes if you were to pursue more advanced chemistry classes. This is an alteration to that formula. To take it from logarithmic to exponential form literally is all it is. It's rearranging the equation. And some students, last year's students, said they by far preferred just this equation. And this equation is the same thing, but instead of solving for pH, it solves for H+. And it's the acid concentration over the salt concentration multiplied by Ka. When I was studying as a student, I would remember it as the A over S times Ka formula, or the acid formula. Like, ask. That's how I would remember it. And that was an easy way. When I was a tutor, that I would help students to remember the formula. But depending on the way the question's framed, this might be the easier formula to work with. It just depends on how the question is framed. But in order to use this formula, you have to know how to go from exponential to logarithmic form and back and forth. So if you are not comfortable with that process, then you would probably be opting for the second equation. So these 2 are the same. You're going to pick which one you want to use for questions. You can use either one because they're literally the same thing. And so one thing I want to talk about before we do practice questions, notice how it says salt over acid. For this formula, salt or conjugate base and acid can either be in mole Dm-3 or moles. Why? When you plug your amount of salt and your amount of acid into here, you can either do mole Dm-3 or you can just do moles, since the Dm cubes cancel out. So they just have to match. Either you're putting concentration here and concentration here, or you're putting moles here and moles there. So that's one of the nifty features of this formula. If they just give you moles of both, you can solve it. If they give you the concentration of both, you can solve it. If they give you a concentration in one and a mole in the other, then you'd have to do a conversion to solve it. So this can either be in mole, cm cubed, or mole. All right, so now that I said that, we're gonna do some initial questions before we're done for the day. Did you all fix it? Did you figure it out yet?
It's less than 25.
What?
It's less
Less than 0.5?
25. It's less than 25.
Of a what? A drop?
Yeah.
How much water have you used? For a test. We don't have that much distilled water today for 11 tables. We'll have to discuss that.
Sorry, guys, I was kind of thirsty.
All right, so let's get to the math. So
And that's all I did was 25.
that is pretty much all I heard. Let's do a couple of practice math questions. First one, calculate the pH of the following buffer solution.
Your birthday, is it soon or?
Circle that. What should I do here? I'm looking for the pH. First, you're gonna pick which formula you wanna use. Raise your hand if you think, you wanna use formula 1. Raise your hand if you wanna use formula 2. Okay, so we're gonna use formula 2. However, you could use formula 1 to solve any question. And H plus equals acid over salt times Ka. I understand why those of you who opted for formula 2 did. We have the Ka. We don't have to do a conversion to pKa. So, given this is the formula, and we know we have to use this because we have a buffer. Do they have to tell you have a buffer? How would you know?
It's an
You'd have to identify that you have a
acid.
weak acid, that it is indeed a weak acid, and you'd also have to identify that you have its conjugate base or its salt, the salt that comes from that. You'd have to identify you have both of those things. All right, ready to continue? You know what? Here's what we're gonna do. We're just gonna cap it at 100 centimeters cubed, Stefan and Sophia.
We just figured it out.
How much?
0.0225.
You're gonna have to explain that. I just hear numbers.
From a gallon to 0.25.
Of a gallon? I don't know. All right, so I have in this question the concentration of acid. Do you agree?
Yeah.
What is it? So I would put that on the top.
No, it's 0.05.
Oh, it's 0.05. I heard 0.1. It is 0.05. I see it.
What kind of hat is that?
Because that would be acid. Okay. What's the salt?
0.1.
0.1. What's the Ka?
You can be like of any one, like
It's got to be for this.
it has to be as the
It
acid.
has to be a bad acid. Absolutely.
What are you doing?
It's that.
Oh wait, yeah.
What do we do now?
What if you give it to for
They won't. And it won't be called a Ka, it would be called a Kb. And then you would need Ka times Kb equals Kw to solve from one to the other, which you were explicitly told in the instructions that they were not going to assess that. However, on an Olympiad, yes, is the answer.
It's plus
Continue. So what would the answer be for 8 plus?
8 times the negative.
What did we say?
8 times the negative.
Does that give you,
Yeah, you guys can connect up a lot.
when you take the negative log of that, does that give you Because I got the answer with the other formula, I chose the other formula. Does that give you 4.1? Because 4.1 is the answer. So why is the pH of this buffer 4 and not 7?
That's more concentration.
Because it's dependent on the
Oh, it's plus.
value of the Ka. Notice that the Ka is to the 10 to the negative 4. Look at what the pH is right around. 4. The Ka is kind of telling you the range of the area the pH will be in for that specific buffer. And the Ka is dependent on the actual acid that you have, whether it's a weaker acid or a stronger acid. Does that kind of make sense? So that kind of gives you an idea of what you're looking for in the numerical range. Ready to try a second one? All right, second one. Similar. Same formula, so keep it simple. H plus equals acid over salt times Ka. What's my acid amount?
0.0100.
0.01. What's my salt amount?
0.04.
0.04. My Ka is 6.3 times 10 to the negative 5. What did that make our H plus?
Uh, 1.6 times 10 to the negative 5.
I get. You said 1.6 times 10 to the negative 5?
That's because I round to the tenths.
This calculator is dying. Is it battery? Because I used the other formula, so.
Wait, Miss, these calculators die?
Yeah, well, eventually they need a battery replacement. Yes. If they start to get really light. I get 1.6 times 10 to the negative 5. Yes?
Yes.
And then pH would be, with the other formula, I got 4.8.
But
Think
for
you get
me,
similar?
it's acid over there. Right here, so it's acid. That's for me.
Okay, think about it.
I have, yeah. No, it's
It
like,
should be close,
it's formula.
but not necessarily exactly 5 in that area. And so you can verify whether or not you're solving these correctly. All right, so that's the level as easy as you could possibly be ever given a question. They cannot make the question easier than this. It's literally, they give you everything you need, you plug it in the formula, that's it. So let's add a complication. How many moles of sodium ethanoates must be added to 1 decimeter cubed of 0.1 molarity ethanoic acid to produce a buffer solution of a pH of 4.9? And they give you the Ka. So first of all, which formula would you like to use? Would you like to continue using the one you've been using, or would you like to switch?
Yes.
If you switch, just remember that I just want to bring this up. This is the other formula. If you switch, you'd have to find something inside of a log. Are you comfortable with finding something inside of a log? I see some yeses, some nos. Because I see some nos, we're going to use the other formula. But you would literally have to change from logarithmic to exponential to solve the question. So I'll use the other one so I don't complicate your life. But just be aware, especially during tutoring, if you want me to go over it, I can totally go over this one, and sometimes this one's more helpful depending on the situation. So H plus equals, I'm looking for moles, but I'm given concentration. Do I freak out? They either both have to be in moles or they both have to be in molarity. If I'm looking for moles, then the other one I should also put in moles. Okay. How hard is that to do? I have 1 decimeter cubed of a 0.1 mole over 1 decimeter cubed ethanoic acid. Does it make sense? that the moles are 0.1?
Yeah.
I have 1 decimeter cubed times 0.1 moles over 1 decimeter cubed, just to reason that out. You have 0.1 moles. Because they intentionally gave you 1 decimeter cubed. 0.1 moles of the ethanoic acid. So this is going to be 0.1. Are we okay with that? The salt is what I'm looking for. And the Ka, I have it. 1.74 times 10 to the negative 5. I also have one more thing I didn't fill in yet. What else do I have? I can't be solving for 2 things. I can only be solving for 1. I have the H plus. How do I get that?
Negative.
So this would actually be 10 to the negative 4.9. So 0.1 multiplied by 1.74 times 10 to the negative 5 over x. Your ability to solve this depends on your ability to algebra. 10 to the negative 4.9 is, I get 1.26 times 10 to the negative 5. Sorry for those of you that don't like scientific notation. I don't want to write all those zeros. And then these 2 are both on the top, so you multiply them by each other. So it's 0.1 times 1.74 times 10 to the negative 5, which is 1.74 times 10 to the negative 6, and x on the bottom. How to solve for x. I don't know if you remember last year, I might have taught you a trick. Whenever you see a formula in this format, you literally can just switch those 2. If x is on the denominator, you can switch it with the number on the other side. It will always work. You could just do the full cross multiplication to figure that out. The full cross multiplication would be put a 1 here and then do the cross multiplication. You would end up with 1.26 times 10 to the negative 5x equals 1.74 times 10 to the negative 6 times 1, right? Then divide both sides by 1.26 times 10 to the negative 5, and it's exactly what I told you. That goes there, the x goes up there. Like it works every time. You have a formula like this. So then you just divide these 2 numbers. What do I have to do when I'm dividing these 2 numbers if I have one of these calculators? I need to use parentheses. If you have the Casio, you already have a numerator denominator thing. So that's one of the things that's nice about the Casio calculator. But if you have these, you have to put parentheses. So let's see, what do we get?
Yeah.
But that's,
Depends on the ability to math. I get 0.138. Moles of what?
What's that?
The sodium ethanoate.
We have to do that.
You have the ethanoic acid. Try to figure out the salt. How much salt to add. All right. I believe we have one more question we're going to cover today. I think the last one I'll wait because I want us to be able to do that little lab exercise. So this next one will be the last one for the day.
No.
That is a reset.
That is
100%.
Nice.
Steph, you okay? Okay, I heard a yes. Thank you, Sophia.
What's the lowest we have this?
9.
Something else.
Mine? No, but like inevitable.
Oh, we don't know. We're just starting this year.
No,
I'm guessing it was like a month.
Over years.
I'm guessing it's like a month.
Oh, month.
Also,
I heard it.
Oh.
I heard it from here.
I did not hear.
Like,
All right. Last question. Let's get to it. You've got a buffer.
So basically,
And-
X will put
They
on.
give you a Ka. And they ask you to calculate. This is the other buffer, one of the other buffers in your cells.
Yeah.
The ratio between these 2. Hey, what are these 2 things? What is HPO42 minus and H2PO4 minus? Which one is which?
First one is conjugated, and one is
The first one is your acid, isn't it?
Oh. I was looking
Because it has one more H plus. Oh, okay, okay. And the second one here is your conjugate base, which you could also call the salt. So far, so good? So what are they asking the ratio for here? Salt over acid. Are you following me so far? So now which formula would be the most appropriate? If I'm looking for the ratio between salt and acid, with the fact that they gave me pH, now we would want to use the first one. You could still use the second one, but the first one's actually going to be much easier to use. So we would want to use pH equals pKa plus log salt over acid. The reason why I felt like I need to address this class now is because in your homework, you are going to have a question where you are asked between the ratio between the salt and the acid. So you need to know when they're asking for the ratio, this whole thing right here is the ratio between salt and acid. That means that the entirety of what's inside of this log is your x. That's what you're solving for. That's the x. So we should have everything else. Do we have the pH? 7.4. Do we have the pKa? We have the Ka, so can we get the pKa? Just take the negative log of 6.31 times 10 to the negative 8. pKa I got was 7.20. So I plug that into pKa. Does this make sense? Because I'm solving for the ratio between the salt and the acid. That whole thing is x. So now here's your math. Here it comes. Subtract both sides by 7.2. You get 0.20 equals log 10x. How do I solve for x inside of here? It would be changed 10 to the 0.2. It's always the base, then what's on the other side becomes the exponent, and then this would be x. So what's 10 to the 0.2 power? It's 1.58. And that's the answer. 1.58. That's the ratio of salt to acid. That means to make this buffer, to have this pH, I would need to have 1.58 times the amount of salt than I have acid. Meaning, what does that actually mean? For every 1.58 moles of salt, I would need 1 mole of acid. Does that idea make sense? That's what 1.58 means. The ratio between this and this, because it's back over 1. So for every 1.58 of one, I would need 1 of the other. And then if I put that together, I'll get the ratio that gives me that much specifically.
That is so cool.
It is. And today you're just going to get practice with making a buffer, but you can actually calculate exactly if you want a pH, a specific pH, like how much salt and how much acid you need to add to get exactly a number of that pH, if it's within the capacity. All right, 2 more questions before we're done. And they're both on this slide. We'll stop at this. How do we write an equation to show H2PO4 minus acting as a base? What do we do? So if H2PO4 minus is acting as a base, what do we want to put it together with? An acid. And what's the simplest variant of an acid we can write? H plus. Don't complicate your life. So what does that become? H3PO4. And you get the mark. That's correct. And HPO42 minus, because it still has a hydrogen in it, even though it's a terrible acid, awful acid, because it's got a negative charge. It's a terrible acid, right? And I mentioned that when you have an acid, last class, I mentioned that each H plus that breaks off is weaker than the last one, right? That has the Ka. that's weaker than the last one. So trying to take the third hydrogen off of what's already starting as a weak acid is gotta have like a Ka that's very small. So it's a terrible acid. But they're telling us it could, in certain situations, act as an acid. Tell us how. So what would I have to put it with? So I would put it with OH minus, a negative reacting with a negative. And then what? What has to happen? To act as an acid, it has to give away an H plus. So you have to show the transfer of H plus from here to here. So you know water is going to be one of your results because OH minus gains the H plus, right? What does HPO4 minus 2 become if it loses an H plus? This is where you got to be careful with the charges. What happens when HPO4 has a whole 2 minus charge? If that's +1, what's its phosphate? The PO4. Minus 3. Does that make sense? So this has to be PO4 minus 3 that's left over. To help justify that, I have it here. Yes.
How could someone make a mistake on that?
How can what?
How could someone make a mistake?
Not recognizing this idea. My most common error that I see students make is they'll write the answer as PO4 minus 2. They'll forget that the H was +1 and that means you have to subtract 1 from the charge. That is the most common mistake that I see. All right. Yes, Andrea. You should write double arrows because it is weak.
So then if we don't, it becomes negative.
Perhaps. All right, so we are done with today's lesson, part 1 of buffers. There is a homework for this. But like I said, I wanted to give you some time to work with buffers. So Sophia and Stefan, come on up. Sophia and Stefan. Come up. All right, because we need to hear what you guys were saying about part 5. So first of all, do you have the papers that you corrected step 5? Do you have those? Okay. So go ahead and pass those out. And while I'm talking. So today what you're going to be doing is you are going to make a simple buffer solution. You're actually going to make it out of sodium ethanoate and ethanoic acid. And so you'll be making a simple buffer. Then you're going to test that buffer's pH by adding base to it. And you're going to test the pH of hydrofluoric acid by adding base to it. And you're going to see which one changes the pH faster, the buffered solution or the unbuffered solution. So you're going to get in your table, same as last lab. You're going to put on gloves and goggles. You're going to follow the instructions, except Stefan and Sophia. Let's talk about what happens. Can you say what happens in which step?
Step 5, when you're supposed to add the ACL, like 1 drop of it, you have to split it up 6 times because it was too concentrated to get it to the right pH. That's what you gotta do.
Or just do the 1 drop, go to 50, recognize you're never going to get it to be the same as the buffer, and then just move on. That's only step 5. Everything else should work perfectly. So when you get to step 5, put a circle on it. If you need us to tell you what to do, we'll come to you. So put gloves on, put goggles on, head to the back, go to your big lab stations. Everyone except lab station 10, that's already been used.
Daniel.
All right, I'm going to stop recording now.